All right. Sorry. So next talk. So r2dec. I'm Giovanni Dante Grazioli. I work for NBS, and I wrote this tool, which is a decompiler for Rodari. So first of all, I will release the new version after the talk. It has a bunch of features that I will show today. I hope some people will like it, and if you like it and you want to improve it, please do. I also want to thank this guy, Elisien, that helped me on rewriting the core, and he did an amazing job with the x86 implementation for detection and stuff. I also want to thank all the contributors for this during this project. You helped me a lot. Even just opening an issue was super, super nice because it means that some people are using it. So I won't explain what r2 is, but I will explain what r2dec is. r2dec is just a plugin. It's mostly written in JavaScript. It has a native core running with its own JavaScript, embedded JavaScript engine. What it does, it tries to convert assembly to some pseudocode or it just tries to, it's not perfect, so if you see something wrong, just report it. And what it does, it extends R2 functionality. Technically, R2 does have some pseudo-C writer, if you want to call it this way, but it's not okay nor working good. So I wrote this one just because I want to make something that works slightly better on that. So a little bit of history. So what I have is I started this project in May 2017. It was pretty different. I decided to use the common approach to the decompiler problem. So you have one plugin per each architecture, which wasn't okay to implement, and was trying just was too hard because each time you have to redo each stuff, so each analysis loop and stuff wasn't kind of not okay, but it had also several pros on this approach. Then I did the first write and the second write the previous month. And I've decided to take the approach in a different way. So what I wanted was something that was completely independent from the data that I had. I wanted to be able to add a new architecture in an easy way without stressing too much on how the analysis loop works and other particular points that you might have to implement during the implementation of the new architecture. I also didn't want to handle any type of binary. I just want to have data from R2 and use it as it is. And I also want to have some nice user, let me say, support. When there is something wrong, you just do something, and magically you can just submit the data without having to share the binary or having issue with that. And I also did a transition because the first implementation used Node.js, but then people told me that it wasn't okay because Node.js is big and maybe you don't want to install on, I don't know, your smartphone or whatever. Then I changed it to duct tape, which is the core that I use for running my JavaScript code. And it's super nice because you can script stuff and add some calls to C code, so I can directly call R2 libraries natively without even have to touch the standard I/O and stuff. So what support it has? It has ARM support, AVR, MIPS, Motorola, PowerPC, Spark, V8, 60, Renaissance, WASM, and x86, of course. For ARM, I will add soon or later the ARM64 support. Sorry about that, but during the write, I didn't have time to port also that one. And for WASM, there is some quirks. It's not completely working, but you will still have some nice output if the binary is not too much fucked up. And x86 right now has the most support because of the work of the other guy. So how to install it? You just run r2pm, install r2dec, and that's all. Just 2 points. For Windows user, you won't have r2pm because r2pm is written in bash and is just a script. People are rewriting it in Go, so once that will be available, you can also launch it. In the meantime, you can just run make into, there is a folder that's named P. Just run make in that folder and magically install also r2dec for Windows. And if each time you update your version of R2, please also rerun r2pm install, again, because there will be mismatch between libraries and the R2 won't load the plugin. So how to use it? So you just run your Rotary session with your favorite binary. You just analyze whatever you want. You can just analyze the function or the whole binary. And then you launch just PDD. PDD is the command to call r2dec, and it magically outputs some pseudocode that it will be improving in the future, but that's like an example. So it has some, it gets some arguments. You can pass them like this, so you will have assembly, blocks, colors, cast, and stuff. You can override the settings that you might have on your laptop during the session, or you can just use the simplified form, which is for example, PDA to print assembly, PDDB to just see the scopes, PDI is, we will see later, is to generate the issues, and that's all. So, and you can also combine them. So you can have like PDD and assembly and I don't know, casts too, if you want to see all the casts, like if it's going to cast something from I don't know, 8-bit to 16-bit and whatever. You can also use what is called in R2 available variables. So if you do eat space and something, you will get all the configuration. With r2dec, you also get the r2dec ones, which means that you can script them into your r2c file. It will magically, automatically load during the session. So if you do just PDD and you have enabled, I don't know, the assembly one, you will just see assembly next to the pseudocode. So it's quite useful. And you also use the screen color and the screen HTML. So if you have one of those two enable, you can just copy and paste, like for example, HTML code directly to wherever you want. So you can just dump stuff. So how to generate an issue? So you analyze something and it crashes. As it crashes, you also get a nice message telling you, oh, it's crashed, please send the report, and you just run PDDI. PDDI will generate a big JSON, and that JSON you just copy and paste or just pipe to a file and upload to GitHub. Quite easy, nothing too fancy. And I had somebody that asked me if it contains user information. No, it doesn't. It just contains the binary information. So whatever is your username and such things, I don't care. It is not in there. But you can just check it by yourself if you need to. And how to debug. So technically, as I said, when it crashes, it just crashes. You just say, oh, I have crashed, please report the bug. But if you want to debug it and make a patch, please use this minus dash debug feature. Sorry, this is the dash debug argument, which will show you the where it's crashing. Right now, it's not telling you from which file is crashing, but it's telling you the line, because I evaluate the strings and without telling which file is, and I'm trying to patch this. So maybe in the future we also tell which file is crashing from. But you can just search for the name of the variable that is crashing, because it will tell you, and you can just search for the line also. So you can just do cross-reference just to understand where it's crashing, or you can just go with printfs and stuff. So I have a demo, simple one. This is not good. So as I said, I load my nice binary, I analyze it. Then I say, oh, okay, let's analyze the main. So I launch PDD. Oh, it's not showing. Okay. Yes. Sorry. Don't know why. Better? Yeah. Okay. So what you will see this nice pseudo code dump. So from the binary, for example, you can see, oh, there's a canary. So there is checking if it's crashing or stuff. For example, you can see that it's trying to get the time. And this is changing the time into local time to get some data, and is checking. Then later on, is checking if that data is equals to 0x27, and you get like a printf saying r2con time or nope. And here, like for example, you can see where's the canary check if the function has failed. So it's really simple stuff. And for example, if it's crashing, as I said before, you just call pddi. Oops. Nope. And you get this big JSON file. That's the one you have to report on GitHub. Just with this, I can patch whatever bug you have. So it's quite nice. It's a nice feature. So design. So normally when you design a decompiler, you want to have do some optimization and stuff. So each time you write one, you will have a plugin for, as I said, for each architecture, which will have its own analysis loop, its own way to parse machine code. It will try to optimize the code, and it will sometimes also try to do some deobfuscation. Like if you have like a bunch of registers that is, I don't know, loading stuff but never used, then maybe you can just remove it and optimize the code by doing that. This was the original, as I said, the original implementation that I had, but then later on I changed. So the new design, as I said, is different. So it's JavaScript based because it avoids a recompilation. So in the same session, if you have a bug, you can just patch it in the file, in JavaScript file, and just rerun the command without even have to close the R2 session, and it magically will run. And it doesn't have to parse binary, so I don't care. R2 just provide me all the information, so it just works. Then I've implemented what they call generic operation, or in the code is also called base. It provides all the basic operation like add, subtract, multiply, divide, rotate, or I don't know, assign or something. It also includes a generic control flow analysis. Then I will show later how we'll do them, but essentially you don't have to care about this. You just throw your implementation there. You just say which instruction is what it's doing, and it magically works. So which means that you also include optimization. So you just run something, and magically you also have them. So you don't have to care too much. And as I said, it has a nice feature to reproduce issues, so PDDI. How it works, so for example, for a generic instruction, you usually have a mnemonic, an operand 1, operand 2, whatever. So for example, for the x86, you have add rux10, so which means that you have rux as destination source, which has the rux itself for a source, and you add 10. How it explains, how it's written then in the code, you have base, add, and operand 0, operand 1, where operand 0 is rux and operand 1 is 10. On Renaissance, for example, you will have XORI 28, R10, R7. In the Renaissance assembly, you will have the register being swapped. So the last one is the destination, the first one is the last operand. So you just swap them, and you will get your nice output. And for example, on MIPS, you will have like S0, T3, and 0 and in the end. And the will do is magically will just generate the optimized code, because if you end, of course, T3 with 0, you will get 0, which means S0 equals to 0. And you have like this quirks also, for example, in x86, when you do XOR, if I do XOR of rux with itself, we will just do rux equals 0. So these quirks are also included. So these are the optimization that I was talking about. So for example, for add, if a destination is equals to A and B is 1, you have destination plus plus. If destination is just equals to A, you do destination plus equals to B. And the same, not the non-optimized form then later. And for example, for XOR, you have A, B that are the same, then destination is 0. If you have A or B 0, then the destination is the opposite member. So how control flows works? So this is how that I detect control flows. It's not just that this is a simplification of the whole loop, but essentially, for example, for a while, you will have this nice output. So you have your address 0, your mnemonic, and blah, blah, blah. And at a certain time, you have this jump at address 2, which jumps to address 9. And then at the address 9, you have a conditional branch. You might also have an unconditional jump, but it's either way fine. So what it means, I said to need to understand that since it's jumping back or it's jumping to the same position, it means that this is a loop, because the execution is from top to bottom. So it means that it's going back, it will reiterate. And if I see like a pattern where it's going after the first jump, it means that this is a while. Usually, you won't file just while as you write in C. You will do the compiler. We optimize it into do loop in do while. So sometimes you will find in the code, in the compiled code, do whiles. Sometimes you find whiles. It depends on the analysis that I've done and how it behaves the code itself. So optimization are tricky to get. For ifs, for example, is different. So usually in C you do if A, I don't know, is greater than B. And it means that to get inside the block, you will have the condition needs to be true. In the assembly, it's not that true. It's not like that. You will have the conditional branch, and the branch says, oh, if A is less equal to B, you have to jump. It means you have to skip the block, which in the decompilation means that that's an if, but the condition is inverted. And if at the end of the if there is a jump and that is skipping some other blocks that comes later, it means that the block that is later on is the else block. So, but I'm quite sure that everybody does that. So how to extend the r2dec? So you need to know, first of all, that there is a path that you have to search for, which is usually local share, Rodari, r2pm, git, r2dec.js. You also need to know that under that path there is libdec arc, and that's where you have to place your new architecture. And you also have to add the name of the new architecture under the arcs.js file. And in the name has to match with the command space asm.arch on Rodari. Why? Because I use that to detect which architecture you are using. So if it doesn't match, I cannot support it. Another thing is you have to give a look also to the developer.md file. It's included in the same folder, or you can find it on that address on GitHub. That includes the template for the basic architecture that we'll show later. And you have to know also that you cannot use outside the r2util the __ internal functions and also the r2cmd. Why? Because I don't want to rely on r2 itself. What it means that if there is some data that I haven't, it means that it may be also required for other architectures. So what I do is just prefetch all the information and then analyze them later. And the analysis in this way, I can also use for example, the JSON data I've shown before with PDDI, and I do not rely completely on R2. So R2 will be called just for fetching all the information, then later on will be analyzed. There's also the concept of context. So you will have a JSON object where you can that you can use and fill with whatever you need for. I use it a lot, for example, for analyzing the, I don't know, the conditions. If you have a condition, usually you have an instruction that tries to understand, like to compare them. So to compare, for example, A and B. And later on, you will have a condition jump saying, oh, if the condition that you analyzed before is, I don't know, greater than something, so is greater than, then please jump to this address. So you can use the context by defining all the information, and then later on using on maybe the next instruction. So how the templates looks like, you have especially as to say, but you have these three magic objects, which is base, variable, and extra. Extra is something that is not really needed, but it has some nice function, like is this a string or not. Variable, it contains all the information that you can use actually to define, like for example, oh, this is an instruction that uses pointers. So if the register is used, then please convert this register to a pointer. So you would make an object, which it could be like, for example, a variable.pointer, and it will just make it return this magic object that we can give to the base object that we will see later. So in the structure, you also have base, as I said, is the generics operation that you can use. And then you have the pre-analysis and post-analysis functions, which can be used to change the data before getting into the analysis loop, or do some post-analysis stuff for reasons, I don't know. You have the local vars, which is another function that it requires to return an array of things. You can return all the information that you might need for, like, for example, if you have defined some local variables and say, oh, this is a local variable, just drop in there, and magically, as I showed before, you will have at the beginning of the decompilation all the all the local variables defined, like I don't know, int I equals 0. I don't know. The same for global variables, and so it will be shown outside like in C, you will have a global variable. Then there will be shown in the compilation if you fill that array. The same goes for arguments. That arguments is the function argument that you are analyzing. So if you are analyzing, I don't know, a function called foo, and he has a bunch of arguments, you can just drop them there, and magically you will say foo requires to get input of, I don't know, an integer and a char. And returns is the return type of the function. So if you during the analysis you say, oh, we are modifying, I don't know, for example, x86 rux, and we are never restoring it. Oh, maybe it's I don't know, a 64-bit value. So you change it, and it will magically do the. We'll say during the decompilation, oh, this is a function foo that returns a 64-bit value. So this is the most interesting one. So you have the instructions. So you fill this for each instruction of the architecture, and you define and you return the base object. And by saying, oh, you have the base, and which is an add in this case, and it gets input of the first operand, the second with the second one and third one, and it will just return all the optimization and stuff. Then you have the parser one. Parser is the command that is used to parse the assembly code. So usually you will have a string which it says, I don't know, add rux 10. And then what you want to do is just split it into tokens and maybe do some analysis there, because, like, for example, in x86 you have, I don't know, pointers that are defined with a word or word or whatever before, or there are some brackets. So you will know that those are pointers, and you just want to make it more complete. So you can just drop under OPD any object you like, and it will be fine. And the only important point is that it has to have the name keyword, because it's used to analyze later the instruction by fetching the name from the instructions above structure. And then you have the context function, which is the context, is the function that returns the context object that is used just once at the beginning, and then you will have the nice object that you like to have during the compilation. Another thing is the instruction object, which is the one that you can see here. So this variable inst is actually this object. It contains like the location of the current instruction. If it jumps, it contains the jump point. It contains the assembly line, the original assembly line. Has an array of strings. If you want to add some comments, because I don't know, it has is a special instruction that you want to know to the user that it does something specifically, you can add a comment. You will have the code one, which is the value that is used to, it is assigned to the function. So for example, when it's called add and it returns this base add object, that the return value will be inserted into this variable. You have the parsed object, which is the whatever is the variable that is used, is assigned to the value that is returned by the parser function. And you have the valid one, which is a Boolean. If during the compilation you know that this variable doesn't need to be shown, you just set it to false and magically want to be shown. You have the string one. The string is used, for example, when you have I don't know, a load to pointer and you know that pointer is pointing to a string. The r2dec will magically do all the cross-reference and just drop the string inside there. So if you know that that's a string and it's allocated, then you just drop, you just change, for example, the assignment instead of the pointer with the string itself. Then you have the function. This is conditional. You just say what is A and B and which type of condition, I don't know, less, greater, or whatever. And when the analysis loop will be working on, it will just change it to whatever control flow will be seen and the condition. And if you sometimes happen that you have some bad jumps, like for example for calls, and you know that call is not technical jump in that case because it's just calling a function and you don't want to mess up the decompilation, you just call this one and magically the pointer of the jump value will be gone. And one more thing is, usually you might have in some architecture some really complex instructions. Like for example, on PowerPC there is this rotate leftward, immediate, then mask insert. This is a really fucked up instruction. What it does is it has a bunch of inputs like a destination source, the shift number, the mask begin, the mask end, which are numbers. From mask begin, from mask end, you get a mask. And what it does, the instruction is get this mask, it goes in end with destination, and everything goes in OR with the result of the rotate left instruction, and that goes also in mask. So how to define this in r2dec? You use the base composed object. So what it does is you define an array of base objects. So for example, in this case, you have the rotate left as the first instruction that it will be evaluated. So I create a variable that is named local and a number, and will be given as the destination of the rotation. Then you will have the source and the source register and the number of bits that you want to shift up. And I will define this as a rotate left of 32 bits, so just to be sure that I not fucked something. Then you will have the base end, and which goes from value 0, and then the mask. So I'm just following this structure and redefine them by using just the base operations. And this ops array will be given as input as the base composed, and during the compilation time, when they will be printed, everything will be there. So you will see the rotate left, the end, and the OR. And that's all. So thanks. questions. So if you have questions, I'm really happy to answer them. If you don't, and you may have later on, just find me out during the conference, and I will be more than happy to answer you. So, thanks. Questions? Nope. Okay. Yep. Yes. r2dec is a really. Oh, sorry. Yeah. So he's asking essentially what is the difference between r2dec and r2dec, the decompiler. So the difference is huge. It means that r2dec is analyzing stuff by itself. It has to give some data. It can analyze the binaries also. So it can have, I think it has embedded the capstone. So it does a bunch of things, and it just does that. What it has is it has an engine behind, which is essentially analyzing the instruction, changing them to some microbes, and then analyzing the microbes. And the output of the analysis of those microbes is used to output all the file. And it is kind of better than r2dec itself. But in a specific way. What I'm trying to say is just r2dec is truly decompiling stuff, and it tries to output some really useful and compilable C code. And it also has like some specific functionality and optimization, like if you have a register that is used multiple times, it will just, and is, I don't know, the register is set to 0, it will just use the 0 itself without showing the register. And it has like, I don't know, if you have like a register set to 0 and then an add, the 0 itself will be used for the add, so it's just moving stuff and doing really some magic quirks on the compilation itself. r2dec, it was not designed to be like that. Not that complexity, not this type of complexity, because it's running on JavaScript and it cannot handle too much data. But it was designed to output something that, for example, if you don't know a specific architecture and r2dec supports it, you can use it to compare it with the assembly to PDDA. So you will get, like, for example, for the fucked up instruction that I shown before. So for this one, since you might not know what RLY my is, you will just see that, oh, it's decompiled in that way. Oh, and now I understand what it is. So maybe it will make more sense. So from my point of view, it will be like more a tool that you can use to decompile stuff if you want. I'm okay. Or to just see, oh, I don't know what this means, and R2 maybe doesn't have the pseudo implemented, and maybe mine does have for reasons, and you can just check it. But if you see something like that, please report also to debug to R2 for Radari.
None.
No. Okay.
Oh yeah. Okay. Great. Another question I would have is, some architectures have control flow specific instructions, like for example hardware loops.
Yes.
If there is such an instruction, it most likely will not produce the kind of pattern that usually loops have, like the jump and the back jump and stuff like that. How do you have any concept of how r2dec will handle these?
Okay, so for example, I will make an example for this use case. For example, I found out, like, on x86 there are some string operation that does, for example, comparison, or will initialize some memory data, and it's just one big line of instruction. And you can re-emulate that instruction by using a loop, as you said. But that instruction itself isn't jumping anywhere. So how to emulate that on r2dec? So the only way to emulate that is just saying that it's jumping on itself. In that way, you will know that is a r2dec will know that is a loop, because jumping on itself is a loop. And you can use then later on decompose object to define a more C-like decompilation, where you can define like variables and stuff. Say, oh, you get this register is used as a pointer. You just move the pointer by one each time, and each time you just compare it with another pointer. So technically it's feasible, because the guy that has implemented x86, for example, has done this, has asked me the same question, and I told him how to fix this, and we have now have some support for those type of string operations. So it's quite nice to also have this feature inside our r2dec. Any other question?
Is there anyone? If not, I'll ask another one.
Okay.
Okay. r2dec and I think Hexrace and IDA as well. When they cannot structure a function properly, like the control flow, they resort to labels and gotos.
Yes.
How does r2dec handle this situation? When
I do the same, because there is no other way to define them. So if you have like some freaky optimized code that does really some jumps that you cannot be defined in anything else that jumps, like gotos and labels, I do the same. And if you have like also some strange operation like in ARM, where you can do like add only if there is a condition, also those will be can be easily translated into if-else, and just negating the condition itself. So if it is I don't know, an add with a negative check, you just say it's equal, and everything will be all right. Okay. I don't know the time, but that's all. Thank you so much. Thanks again, and please do some contribution on the project if you like, and if you like also, please use it. Thank you all.